Hi everyone, welcome back. Today we're doing unique Morse code words. The International Morse Code defines a standard encoding where every single letter is mapped to a series of dots and dashes. So A is mapped to dot dash, B is mapped to dash dot dot dot, C is mapped to dash dot, and so on. And for convenience, the full table of the 26 letters is given below, where the first position maps to the Morse code for A, and the last item over here maps to the Morse code for Z. And given an array of strings words, each word can be written as a concatenation of every single character's Morse code. So after we convert each of these words into Morse code, we need to get the number of different transformations across all words. So for example, if we're given 4 words, Jin, Zen, Gig, and Message, then in this case, the transformation of Jin and Zen would map to the same string, and Gig and Message would map to the same string as well. So in this case, there are 2 different transformations, so we return 2. For the second example, words is an array of one single word, so we return 1. For every single one of these words, we have up to 100 of them and a minimum of 1. And every single word can have up to 1 to 12 characters. And finally, every single word consists of lowercase English letters. This question and the approach for it can be broken down into 2 steps. The first step would be to figure out how to convert each word into a unique Morse code. And the second step is to deduplicate it. So with that, let's get started with the first step, converting every single word into a unique Morse code. So this problem of converting each word into a unique Morse code can be broken down further into 2 steps as well. The first step would be to get the corresponding Morse code for a given character. So to do that, we can copy this table and define a string array which would contain all these mappings. So let's call this table, and this will be equals to this representation over here. So just like this. And the next step would be to figure out how we can convert a character into an index, which we can use to map to each of their unique Morse codes. So for example, A will be expected to be mapped to 0, and we can use 0 to get this first mapping. So to do that, let's define a function, or to be more accurate, a method in class solution. For our viewers who are new to this concept between functions and methods, methods are a type of function, but it is strictly defined under a class. So over here, let's define a simple method that is a public static integer. We want this function to return an integer, and we want this function to be able to be called without needing an instance of object solution. So let's call this get char table index. We will take in a character, input character, and we will return an integer where A is mapped to 0 and Z is mapped to 25. To do this, we'll be using a property called the ASCII table. So everything, all data in our laptops are represented with numbers, to be specific, binary numbers, since a laptop is pretty much made of just bits. So we have to figure out how to convert a character into an integer. So in this case, this is one way which we can do that. So in this case, if we cast a character A into an integer, then we will get the number 97. So with this property, what this means is we can technically get this mapping by casting the input char into an integer, and we subtract it by the casted integer of the character A. So since A will give us back 97, if we pass in A, it will be 97 minus 97, giving us 0. That's for A. And if we pass in B, then this will be 98 minus 97, giving us 1. So this is pretty much the implementation that we want. So using this, we can now start to iterate through every single word we're given, and we will iterate through every single character to get the char table index. Using this char table index, we will get the unique Morse code, and we would append it to one single string, that we will add into a data structure to deduplicate for us. So that was a lot of words. So let's get started with that. So we will iterate through every single word like this. And for each of these words, we will use an index to assess that character. So we will start off with index equals to 0. And we will want this loop to continue until we get the length of like pretty much from 0 to the index right before the end of the word, and index plus plus. So using this index, we can get the current char. Current char equals to word.char@index. So to recap, char@, is a string method that takes in an index and it returns back the character inside a string object. So this string object is over here. So now that we have this current character, let's get the char table index. So this will be equals to solution.get char table index, and we will pass in the character that we got on line 15. And now using this index, we can get the table. So let's get the Morse code char, and this will be equals to table at this specific index like this. Now that we figure out how to get each character's Morse code, now the next step would be to learn how to append this into a string. So unfortunately in Java, strings are immutable. So what this means is whenever we add A to B, we are really creating a copy like this. Because if you cannot mutate or change a string, then the only way to add a string is to create a copy and add both A and B into it. So what this means, if you have a word that is, let's say 10 characters long, and you form it character by character, let's try 5. So if we do A plus B, then this is going to take 2 operations. So let's say A over here, creating A would be 1 operation. Creating AB would be 1 operation to copy A and 1 additional operation to add B to this. So this is going to be 2. ABC would be 2 operations to copy A and B respectively, and you get the pattern. So A, B, C, D, in this case there'll be 4 operations to create it, and finally A, B, C, D, E, this would be 5 operations. So if we sum up all the operations, that would be 15 operations. And to be specific, the pattern for 1 plus 2 plus 3 and so on and so forth is n multiplied by n plus 1 divided by 2. Or if we express it in time complexity, the time complexity of concatenating a string of length 5 is O(n) squared, where n is equals to 5. And that's not nice. We want to avoid that. So to do that, we can use a StringBuilder. A StringBuilder is an object which allows us to add these characters inside a list under the hood like this. So when we append characters, we are really adding characters into this list. And once we are done, if we call toString on this StringBuilder, it would copy every single content only at the end during string formation. So this would give us O(n) time. So this is way more efficient compared to string concatenation. So I hope this was clear. So what I'm trying to say is, when you want to append to strings, please use a StringBuilder, because you're going to take your time complexity from O(n) squared to O(n). So let's define a StringBuilder. So StringBuilder sp equals to new StringBuilder. So using this StringBuilder, we're going to append every single one of these Morse codes inside here. So we will append it here. And after this for loop, after we iterated through every single character, we will convert this into a string. So let's call this word transformation equals to sp.toString. So toString is also a method under the StringBuilder that converts all contents in the StringBuilder into a string. And now that you have the word transformation, we have to figure out how do we deduplicate these word transformations for every single word. One way to do that is to use a HashSet. So for our viewers who come from Python, that's analogous to set. So similar to how set in Python is capable of deduplicating items, similarly a hash set does the same as well. So let's define a hash set. If you're curious, the hash set is from java.util.hashset, but because Leetcode has already imported them for us by default, we don't have to import it. So in this case, we want this hash set to contain strings where every one of these items is a word transformation. So let's define unique Morse representations equals to new hash set like this. So now that we're done, we would add this word transformation into this hash set. And once we're done, we will return the size of this hash set. And that's pretty much it. Let's trace this to see if we have any mistakes here. I don't see any mistakes, but it always bites me whenever I think that's the case. So I'll just check to be sure. Okay, so in under interview fashion, I'll be showing how we can trace our code quickly to ensure that we do not have any logical errors. So let's use this test case over here. The first test case, words, gins, and gig message. So let's first trace out the state of this unique Morse representation. Let's use this to represent a new hash set. And let's set the word to the first word, gin. So the string builder is going to be an empty string builder, and I'll represent it like this. And we are currently looking at index 0. So using this index, we get G, current char will be equals to G, and the char table index in this case would be G minus A. So G in this case, let's take a look at the ASCII table. G would be 103. So 103, A equals to 97. So this would give us 6. So 6 would be 0, 1, 2, 3, 4, 5, 6. It would be this representation over here. So this is for G. Okay, this would be equals to 6. And this will be equals to G. Okay. And just to be sure, take a sneak peek at the test case. Okay, that looks fine. So we are adding this into our string builder over here. And let's move on to the next character. So I in this case would be 105. Another way under technical interview conditions would be to count from A, 97, 98, 99. But since we already have the ASCII table here, why not? So now we have 105 minus 97, so this gives us 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So 2 dots over here, and we will append this to our string builder over here. So we get this. So is it dot dot? Is it dot dot? Yes, looks like it's a dot dot for I. Finally, we reach the last character, thank goodness. N is 110. So 110. 110 minus 97, this gives us 13. So this is 13. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's this over here. And this would be this. So we will append this to the string builder. We will call toString on the string builder, and we'll get dash dash dot 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 dash dot. So this is pretty much the answer for gin. So we get this. Yep, looks great. So we will append this into the unique Morse representation. It's really quite a pain, so I will be skipping the other 2 words that we have, but you get the idea. This is pretty much how our algorithm will work. So we will get back size 2, but let's run this code to see if this passes our test cases. So this passes, thank goodness, and let's run this. Okay, so this passes. Let's talk about the time and space complexity. How does the worst case time and space usage of this algorithm scale with the size n? So if we let n to be the number of words in string, then the time complexity in this case In this case, defining a hash set is O1. Iterating through every single word is ON. If we have more words, then there's more words to define. So this string builder over here is going to be defining is O1. And we're iterating through every single character over here. Let's specify M to be the number of characters in each word. So this is going to be OM. The more the more characters that we have, the more expensive this will be. So fortunately, getting a character from a string, in this case is O1. So this is O1. And getting the character table index, in this case, this function here is also O1 as well. It's very cheap. And getting an item from a hash table, in this case, let's just have an amortized or rather average time complexity of O1. Let this be O1. So this is pretty much O1 for all these three first operations. Morse code char, in this case, appending it to a string builder is also O1. So in short, every single iteration is O1, and the overall time complexity for this is OM. Converting the string builder into a string, unfortunately, this is going to be OM. Understandably, in the string builder's implementation, the only way for it to reconstruct a string is to reiterate through every single character inside this string builder. So this is going to be OM. And adding it into a hash set is going to be O1. So this is pretty much ONM, to be specific, it's O2MN. But since we remove the bases, it's going to be time complexity OMN. This is going to be O1. Checking the size we can set the size to be an attribute and increment it every time we add an item to the hash set. So that's pretty cheap. For the space complexity, let's remove all our workings for time complexity. And over here, since this hash set would contain, in the worst case, if we are given we are given words with unique word representations, this can be up to ON. Yes. And you can argue it's ONM because the longer the string, the larger the unique Morse representations will be. So you can say it scales with respect to M as well. String builder, we are reusing it, so we would reconvert this into a fresh string builder. So this would be OM. And in this case, these temporary variables, index, current char, all this stuff here would be constant memory. They'll be reused again and again. So this is pretty much O1. Word transformation, unfortunately, this copy would be OM as well. And adding it into this table here, I guess it's already counted here. But in summary, the space complexity is going to be ONM plus O2M. But because we will remove all higher bases, we will remove this, and the space complexity is going to be MN as well. So that's pretty much it for this question. I hope this was a clear explanation. If you like it, please give us a like and subscribe, and we will see you in the next video.